This is a quick game theory review of material that should have already been learned from your prereqs for this behavioral economics class. So first up, we have the Prisoner's Dilemma game, probably the most famous game in all of game theory. What's notable of the Prisoner's Dilemma game is that we have it as a dominance solvable game. So there is strict dominance in this game. Player 1 always prefers to cheat, and player 2 always prefers to cheat. And so we end up at this equilibria down here of 1 and 1. Notice that this is Pareto inferior to the cooperate outcome, and yet nonetheless we still end up with a pure strategy Nash equilibria of this 1-1 cheat outcome. The reason for this is that we have that strict dominance. So we can look at player 1's options. Player 1 can say, well, if player 2 is going to cooperate, if player 2 is going to be in this cooperate zone, then me as player 1, I can either cooperate and get a 5, or I can cheat and get an 8. So obviously what I'm going to do in this situation is I am going to cheat. So player 1, I'm not going to play in this area here, because I also know that if player 2 is going to instead play cheat, that I also have a situation where I could either cooperate and get a 0 or cheat and get a 1. So in both cases, what's happening is that my cheat payoff is higher than the corresponding payoffs I would have gotten if I were to cooperate. And so there's no way that I am ever going to play cooperate if I am player 1, right? And we can do the same thing for player 2. We can look at player 2's options here. We can say, all right, well, player 2, let's look at your options here. If I have player 1 cooperating, then what's happening here? Well, I can either score a 5 or an 8. The 8 comes when I cheat. If player 1 cheats, I can either score a 0 or I can score a 1. Well, in both cases, right, the cheat payoff is better. So I'm never going to play this cooperate option here. So we're never going to play cooperate because in both cases, it's strictly dominant. It's always better for me to cheat. So player 2 is never going to play these options. So what we ended up with is player 1 is never going to play this option, never going to play this option. Player 2 is never going to play the cooperate options either. And so where we end up is we end up with this equilibria down here of this 1-1 outcome, right? So we have this 1-1 equilibria. It's a pure strategy Nash equilibria. In this game, both players have dominant strategies to cheat, right? That's really important. And then also what we see is that this outcome, the cheat outcome, is a pure strategy Nash equilibria. No one would like to move, holding everyone else's actions constant. However, it is Pareto inferior to the cooperate outcome of 5-5, right? So it's Pareto inferior, meaning that we would end up with at least one person being worse off without anybody being made better off in this move, right? So we could make both players better off by moving to the cooperate outcome, right? So it's got this Pareto inferior element to it as well. So that is our Prisoner's Dilemma game. So next up is the public goods game. In a public goods game, you have a number of players. Here we have 4 players who are all starting with $20. And what they can do is they then are asked to contribute to the public good, to the kind of communal pool. And what we do is we see that the players can contribute some amount of money. And the reason that they would contribute to this public pool here is because that money is then multiplied by some amount, in this case by 1.2. And then it is turned into the new public pool amount and then equally distributed to all the players. So we get this equal distribution of those payoffs into this. So the basic idea from this is that what we would like to have is some kind of public good, say like national defense. All of us contribute some amount to national defense. And then what happens is that good is actually worth more to us than the combined amount that we contributed, and so we get this higher value, and then it's equally distributed to all of us. And so that's why we would want to contribute. However, as these public goods games go, basically what happens is you get a group of individuals and you say, hey, how much would you like to contribute? Knowing that what we're going to do is multiply how much the total of the total contribution amount by some multiplier here. And then what we're going to do is we're going to equally split these up. So what happens here is that the group payoff is maximized when everybody contributes all of their money. And yet, it is strictly dominant to contribute 0 of your money. Right? So it's strictly dominant to contribute 0, even though it is best for the group if everyone contributes all of their points. Right? And so what happens is we can see kind of different types of players. So these 3 players here, they all contribute all 20 of their dollars, which leads to $60 total being contributed. Right? This player over here contributes nothing. Right? They don't contribute anything. So we end up with $60 total being contributed. We multiply that by 1.2, and that gives us $72 worth of value from this public good. We then split that up equally among all 4 individuals in the society, and we can divide that up, and that sends back $18 to each individual. So player 1 ends up contributing $20 and getting back 18. Player 2 the same, player 3 the same, but player 4 over here, right, contributed nothing, gets $18 in return, so they keep their 20 plus the 18 that they got, and so they end up with $38. So no matter what the other players do, it is better for you to contribute 0. It's strictly dominant for you to do 0 contribution. Even if you contributed all 20 of your dollars here, right, what will happen is you are not going to get the full 20 back. You are going to get 20 times 1.2 divided by 4 back. And so it does not make sense for you to make any contribution. Nash play is to contribute 0 to the public goods game, even though the group payoff is maximized when all players contribute all of their points. The standard setup of the Ultimatum game is that player 1 acts first. So we have player 1 moving first up here, right, moving from top to bottom, and they can create any kind of distribution that they would like, ranging between $10 and 1 penny being offered to player 2. So player 1 starts with $10 and can either can divide up this $10 between player 1 and player 2. So there's a continuum, a distribution of how much money they give to player 2 and how much money they keep for themselves. Player 2 then acts at the second stage of the game and then can either accept the offer of that distribution, and player 1 will get $10 minus whatever that offer is. So say the offer is $3. If the offer is $3, player 1 then gets $7 and player 2 gets the $3. Right? But this is only if player 2 accepts the offer at stage 2 of the game. The other option for player 2 is to reject the offer at stage 2 of the game. So if player 1 puts forward a distribution that is $7 for player 1 and $3 for player 2, player 2 could reject this offer, and then player 1 will get $0 and player 2 will get $0. Right? So player 1 makes a distribution between the $10, and then player 2 either accepts that distribution or rejects it, and both players walk away with nothing. Right? So in this case, we have an ultimatum, a take it or leave it situation. The standard game theory solution concept for this is through kind of the logic of backward induction. For player 1 to offer the lowest possible offer, in this case, say 1 penny, and to keep $9.99 for themselves, and then for player 2 to accept that offer. So with the standard game theory approach, any positive sum amount is better than 0. So player 2 is better off taking a penny than getting nothing. And so player 2 should always accept a penny if it is offered to them. Player 1, knowing that this would be the case, that if player 2 is offered a penny, she will take it. Player 1 should then offer the lowest possible amount to keep the highest possible amount for themselves. So the standard game theory solution here, it is kind of a dominance backward induction solution concept here, where a minimal offer is made by player 1, the lowest possible offer is made by player 1, and then player 2 will accept that offer, and player 1 will end up with the highest possible payoff that they could get, and player 2 will end up with the lowest possible payoff, other than if they rejected the offer and ended up with 0-0. So in this case, the example that I gave, player 1 would get $9.99, and player 2 would walk away with a penny. The Dictator game may be a new concept from intermediate micro students, but it is really essentially the Ultimatum game, but with a little twist. Player 2 does not get the option to accept or reject. Player 1 is plain and simple, just the dictator. Player 1 comes up with a distribution, and then player 2 automatically is on this acceptance of the offer. Right? So player 1 can offer anything that they want, and player 2 automatically accepts that offer. So here again, the standard economic solution for this would be the exact same as the Ultimatum game. Player 1 will offer up the lowest possible amount, a penny, and then player 2, by definition, accepts this offer. Right? So here again, if we had this same setup, we would have an offer of $9.99 and 1 cent. And player 1 would end up keeping $9.99, and player 2 would get 1 penny, or the lowest possible offer, depending on what the game's rules are. So this is the Dictator game. Basically the Ultimatum game, but stage 2 of the game is not an option for player 2 to reject. It doesn't exist. So it's an Ultimatum game, but then player 2 doesn't have an option at stage 2. Here we have the classic Hawk-Dove game. In this game, there is no strict dominance. So this is a little bit different than the Prisoner's Dilemma game, where we do have an outcome that has strict dominance. So what we can see within this game is that player 1, if we look at player 1's options, we can say, okay, well, you know, if player 2 played Hawk, I would get 0, and if I played Hawk, and 1 if I play Dove. So it looks like Dove's better. However, if player 2 plays Dove, then what happens is I get 7 by playing Hawk and 4 by playing Dove. So if player 2 does this, me as player 1, I'd like to do Dove. If player 2 plays Dove, then me as player 1, I would like to play Hawk. So it's not strictly dominant for me to play either Hawk or Dove, so we don't learn anything from that. And player 2's logic would work out exactly the same. We would have this payoff here and here being better. So player 2 is better off playing Hawk if player 1 plays Dove, and player 2 is better off playing Dove if player 1 plays Hawk. Right? So we don't know what really to play in this situation. What we do end up with, however, is a couple of different solution concepts. So this brings into play non-strict dominant solution concepts. And so we have a couple of different ways we can solve this. What we have in this situation is a mixed strategy Nash equilibria, and then 2 pure strategy Nash equilibria. So you can find pure strategy Nash equilibria simply by going through every cell in the game and seeing, would anyone like to move given the other player's action held constant? And if no one would like to move from that situation, holding constant the other player's actions, then we have a pure strategy Nash equilibria. So what we can do is we can say, all right, let's look right here. Hold player 2 constant. So player 2 is definitely playing Hawk. And we're thinking about this first cell right here. So we're considering this cell right here. Player 2 is definitely playing Hawk. Do I, player 1, want to change my strategy? The answer is yes. I want to change my strategy. So there's no way that this cell 0, 0 is a pure strategy Nash equilibria. Now what we can do is we can go to the next cell. So we can go here to this cell. We can say, all right, let's hold player 2's actions constant. Player 2 is playing Dove. Do I, player 1, want to change my strategy from this payoff of 7 down to this payoff of 4? And the answer is obviously no, I do not want to change my strategy. So this potentially is a pure strategy Nash equilibria. As player 1, I do not want to move, holding constant player 2's actions. But we also need player 2 to not want to move, holding constant player 1's actions. So now let's say player 1 is held constant. That player 1 is definitely playing hawk. Does player 2 want to change their strategy from dove over to hawk? Does player 2 want to move from this cell over to this cell? Does player 2 want to change their payoff from 1 to 0? Obviously the answer is no, they do not want to. And so what we get here, again, is player 2 not wanting to move, holding constant the actions of the other individuals. And so this payoff is a pure strategy Nash equilibria. So this cell right here, we do have a pure strategy Nash equilibria. So that's one solution concept. However, in this game, this is not the only pure strategy Nash equilibria. The same logic holds for cell 3. Right? Player 1 does not want to move, holding constant player 2's option of hawk from this cell right here. And player 2, holding constant player 1 playing dove, does not want to change their strategy from 7 over to 4. And so this cell here, following the same logic as the last one, is also a pure strategy Nash equilibria. This cell down here looks like it might be a pure strategy Nash equilibria, but we can see what's happening here. You can hold player 2's action constant as dove. Does player 1 want to change from playing dove up to hawk? The answer is yes, I do want to leave this cell. And if the answer is yes, I'd like to move holding someone else's actions constant, we do not have a pure strategy Nash equilibria. So here we have two solution concepts, and it introduces this idea of a pure strategy Nash equilibria to us. Both of those are solution concepts. Now, when we have no pure strategy Nash equilibria or multiple pure strategy Nash equilibria, we also have another solution concept called a mixed strategy Nash equilibria. And a lot of times what we'll do in a hawk-dove game is we would model the optimal behavior of each individual as playing a mixed strategy. Right? So we want to play a mixed strategy Nash equilibria in this hawk-dove game. When you play a mixed strategy Nash equilibria, what you do is you choose a behavior or play a mixture of your options that leaves your other opponents indifferent. You make your opponents indifferent in order to eliminate any behavioral patterns that they could exploit. You take on a strategy where your opponent's strategy choices cannot create strictly better outcomes by changing. So your goal is to play a mix, right? So you can think of playing rock, paper, scissors. You're going to optimize by mixing up your strategy, by having it play like as though it's random, as opposed to playing one action more often than others. So then your opponent could kind of pick up on that and take advantage of it and do better. So to review these little bit more challenging solution concepts, the concepts from the hawk-dove game of the pure strategy Nash equilibria and the mixed strategy Nash equilibria, I have a couple of follow-ups on this. You should be able to look at this question here and say, okay, identify the pure strategy Nash equilibria, right? A pure strategy Nash equilibria is this set of player strategies is a pure strategy Nash equilibria if and only if no player could do strictly better by changing their strategies, holding all other players' strategies fixed. So which of these outcomes are pure strategy Nash equilibria? Again, you can have one, multiple, or none of these be pure strategy Nash equilibria. So go ahead, pause the video, and see if you can solve this. So this would be the solution concept here. We have two pure strategy Nash equilibria. Both the 4-4 quadrants are our pure strategy Nash equilibria answers to this. So make sure you understand that solution concept of a pure strategy Nash equilibria. And again, see that in the hawk-dove game, we had two pure strategy Nash equilibria, the 1-7 and 7-1 payoffs. And then we can also look at mixed strategy Nash equilibria and actually do the calculations. So again, this is something you should have done in an intermediate micro class. But what you can do is you can try and find each player's mixed strategy Nash equilibria. So in this game, we're going to try and find player 1's mixed strategy Nash equilibria Player 1 is always listed over here on the left, and player 2 is always listed on the top in this standard kind of format. So we're looking for player 1's mixed strategy Nash equilibria. So what player 1 can do is they can say, okay, well, I can think about how often will I play up versus how often do I play down. So I could assign this likelihood that I play up a probability of P, which means that I am going to play down at 1 minus P. Right? And so we can think about it that way. Say, okay, well, what's really happening here, though, within this basic setup? All right, and so what am I going to do is I need to make it so that player 2 is indifferent between playing left and right, given the probability that I play up at P and down at 1 minus P. So I am only going to look at player 2's payoffs for the situation of figuring out player 1's mixed strategy. And this is where students usually get a little bit caught up, because we want to think, well, what do I want to play? I need to look at my payoffs. And it doesn't really matter what my payoffs are, because player 2 is going to act according to their payoffs, right? And so what we can do is we can say, all right, player 1's payoffs do not really matter so much here. We're only going to be looking at player 2's payoffs, the second payoffs that are actually listed here. And what we need to do is leave the left, playing left, equal to playing right. So that's what we're looking to do here. So what we can do is we can say player 2 could play left and score 20 points. Well, when would they score 20 points? Only when player 1 plays up or at P. So player 2 would get 20 times however often we play up P. So 20 times P gives you that 20P. And then they can add to that the payoff that they get from when player 1 plays down and player 2 plays left. So player 2's left payoff is going to be this 20 times P plus this -5 times 1 minus P, right? And so we get this 20P minus 1 or -5 times 1 minus P, right? That'll be the payoff for player 2 for playing left, right? They're either going to get 20 or they're going to get -5. How often are they going to get 20? They're going to get it however often player 1 plays up. How often are they going to get -5? Well, the 1 minus that probability. All right, so that's the payoff for player 2 playing left. And player 2 needs to be indifferent between playing left and right for a mixed strategy Nash equilibria. And so then we can say, what's the payoff for playing right? Well, they're going to get 10. How often are they going to get 10? Depends on how often we're in this up category here, probability P. Plus, they're going to get 0. How often do they get 0? Well, it depends on how often player 1 plays down, so that 1 minus P amount. So we do 0 times 1 minus P gets added to that 10 times P, and that's the payoff for playing right. We set those two equal to each other, and what we get is player 1's optimal answer for the P variable, so whatever the probability for playing up is. And then that also gives us our probability for playing down. That will leave player 2 indifferent in their behaviors. Similar to a game of rock, paper, scissors, we want to leave our opponent indifferent so that they cannot take advantage or exploit any of our patterns that we have or any of our strategies that we have. And that will allow us to get our maximum possible outcome. So our mixed strategy Nash equilibria in this case is to play up with a probability of 0.33333 and to play down 0.666667. We can also then look at the mixed strategy Nash equilibria payoffs. Now this might be an extension from your intermediate microeconomics class, but the logic doesn't have to go very much further than what you already just did on the last slide. So what we're trying to do in this situation is say, okay, if player 1 played their mixed strategy, what do they expect to get as a payoff then? Like how many, what's the payoffs that they would expect to get from playing this game? What's the expected value of that mixed strategy? So what you do is for each cell, you multiply the probability that player 1 is there by the probability that player 2 is there to get the probability of this cell. So what you need to do is you need to go through and solve, as we did on the last slide, the mixed strategy Nash equilibria for player 1. And then you get the probability of playing up, which gives you the probability also of playing down, 1 minus p. Then what you have to do is you have to solve for player 2's mixed strategy. And you do that the exact same way, but you just assign playing left a probability of p and right 1 minus p. And then you look at player 1's payoffs. So you're going to come up with a mixed strategy Nash equilibria for player 2. And in this case, I just gave that to you as playing left at 2/3. So you can check, you can do the math and see that this would be the case, that player 2 should play a mixed strategy Nash equilibria of left 2/3 of the time. So what you have to do is you have to know that if we have these probabilities, then if we're in up and left, right? If this is our payoff, then we're in this cell. Well, how often does that happen? Well, player 1 plays up 1/3 of the time, and player 2 plays left 2/3 of the time. So we multiply that by by each other, and we end up with a probability that we're in that cell. Okay, so we get the probability that we're in that cell. Whereas, say for this cell here, where player 1 plays up and player 2 plays right, this cell right here, how often are we here? Well, player 1 plays up 1/3 of the time, and player 2 is going to play right 1/3 of the time also, right? Because they play left 2/3 of the time, that means they must play right 2/3 of the time. So you multiply 1/3 by 1/3, and you get the outcome for that cell right there. So in that case, your probability that you're in that cell, you can go through as 0.1 repeating. So 0.3333 times 0.3333, and you end up with a probability of 0.1 repeating, whereas in this cell, we had 0.2 repeating. And you do that for the same thing here. We're going to be here 2/3 of the time, and we're going to be here 2/3 of the time. So player 2 is going to play left 2/3 of the time. Player 1 is going to play down 2/3 of the time. And when we do the math for that, we say, oh, we're in this cell, 0.4 repeating as our estimate there. And then we can look at the right down payoff, and we can say, okay, player 1 is going to be here 2/3 of the time, and player 2 is going to be here 1/3 of the time, or is going to play right 1/3 of the time. So we can multiply those probabilities by each other, and we end up with a 0.2 repeating, right? And again, this is because player 1 is going to play down 2/3 of the time, and player 2 is going to play right 1/3 of the time. So we'll end up in this quadrant 0.2 repeating % of the time. So that's really kind of stage 1 of this process here. For each cell, we multiply the probability that the player 1 is there by the probability that player 2 is there to get the probability of this cell. And then what we do is we multiply the player's payoff by the corresponding probability of each cell, right? And so in this case, we can look at their different payoffs that we have, and we can see what we have. So let's look at player 1 in this cell up and to the left. We're going to be there 0.2 repeating % of the time there, so 0.22222, and we multiply that by player 1's payoff, which is 5, so 0.22222 times 5, and you get this payoff of 1.1 repeating. And then for this cell here, up and right, we're there 0.11111. The payoff is 10, right? So if the payoff is 10 and we have this 0.1111, or sorry, this 1/3, or sorry, this 0.1 repeating % of being there, what we end up with is this 1.1 repeating payoff again, actually, because the payoff is higher even though we're there a little bit less likely. And we can look at this for player 1 again. The payoff is 10, but now we're there 0.4 repeating. So 10 times 0.4 gives player 1 a 4.4 repeating payoff. And then obviously here in this last quadrant, The payoff is 0, so 0.2 times 0, and we get a payoff of 0. So player 1 is going to end up with a 1.1 payoff from up left, a 1.1 expected payoff from up right, and a 4.4 expected payoff when the outcome is left down, and a 0 from right down. We add all those together and we get the expected payoff for player 1 as 6.7. Then we can do the exact same thing for player 2, and what we end up with is a 4.4 repeating here, a 1.1 repeating here. Just by taking 0.1 times this 10, we get that 1.1, right? We got this 4.4 by multiplying 0.2 times 20. We get that 4.4. And then we have this negative payoff down here. So we get this negative 2.2 repeating. We're there 0.4% of the time, or 0.4 as our probability repeating times this negative 5. So the 0.4 repeating times negative 5 gives us that negative 2.2. And then here in this last quadrant, again, we have a payoff of 0. So the expected payoff there is going to be 0. We have to add all of those numbers together. So we get 4.4 plus 1.1 minus the 2.2 repeating, and player 2 gets an expected payoff in this game with the mixed strategy Nash equilibria of 3.3. So you want to kind of add this to your ability in game theory to calculate the mixed strategy Nash equilibria expected payoffs, as you can do a lot with this in game theories problems with mixed strategies.